Okay, so we're basically just given this thing of the video recording at the try today. This is not the most important lecture we have of the semester or anything like that, but I know that Scott and Joe at least wanted to have things like this for reference, and we want to make sure, well, like what things work and what don't. Like, I doubt they can actually read what's on the board when it's on the video, although it's hard to guess, it's HD. But more importantly, can they figure out what page we're on? When I highlight things, can they see it? The little screen itself that's on the back, Jared is peeking at the camera, the little screen that's on the back only has like 180 by 100 pixels or something. You
can read it.
Well, it's very, very tiny. It's like an old-fashioned cell phone. Anyway, so we'll see what it looks like, and that's kind of what the deal is. Okay, so here's the deal. We are on the last section before our test, and it is not my favorite section. It is, I often think that sometimes people who write textbooks, they go like one step too far. You know, they take everything and they just go a little bit too much. In this case, I don't think for the purposes of a, whatever the title of the course is, brief calc or whatever, we needed to go quite this far on the whole business of limits. But that's okay. It's not going to freak me out that we're doing it. It's just that this is not, you're going to see the assignment is smallish. Then, on Thursday, we have a review session. Then I believe this Friday is an early day, not a college day, right? So we don't meet on Friday, which means the test will be on Tuesday. Okay? I am weighing the pros and cons of, see, we have a makeup day coming up. Our first of the snow days to make up is coming up. And I'm weighing the pros and cons of making it a take-home test. I need to talk to the people who know more than I do about, like, oh no, that's actually too far. They don't want the virtual days to be tests or whatever. But I mean, it would be open book, open note. I don't really understand how it makes much difference. Does that make sense? So I'm going to find out. In which case, we would just do something different on Tuesday, like start the next chapter or whatever. But I think Tuesday is the day I'm supposed to give you the assignment for the makeup day for the snow. Of course, we might have more snow days between now and then because weather patterns are coming.
Well, you're a weather person.
I am, but this is an extremely complicated weather pattern. I mean, I don't think anybody has any idea. We could get 5 inches of snow or we could get nothing. These are very, very narrow bands of snow that are setting up and freezing rain. And I mean, the difference between what's going to get a ton and what's going to get basically nothing is going to be 10 miles. You know what I'm saying? I mean, it's just too far, and we can't predict. That's why on the weather map this morning, there's like this giant area of pink on the map that's like wintry mix. That's how the weatherman says we don't know. Okay, it's good. And these are just these narrow. This kind of weather system makes these narrow bands of freezing rain.
Is that what a winter advisory is?
The winter weather advisory is basically they're warning you that there's going to be winter weather, and like winter weather advisories are mostly for planning purposes, for like emergency management and snow plows, and also like dispatchers of semi lines and stuff like that. There's not much the public does with that information. But yeah, we're under a winter weather advisory because if you're like a long-haul trucker, or you're going to go through places, they get a lot of snow. Okay, you need to start planning about things like how you're changing your routes and stuff like that, or whatever. Anyway, so yeah, so this storm, we could get nothing or we could be buried. It's going to be really hard to tell. And whatever we get, it's going to be altogether different 15, 20 miles down the road. I mean, it's going to be crazy. Anywho, I love those kind of weather patterns. I'd love to talk about that. But we got to talk about the formal definition of a limit. And I checked, and in the documentation that comes from EVSC about congratulations, you're teaching calculus or whatever, yeah, we do have to cover this block of material. But there's no guarantee we have to like do a ton with it. So let me show you what's going on here. You know, everything that we've done so far with this idea of limits has been a little bit touchy-feely. I mean, it's kind of been like, take a look, you can see the graph does this, and then the graph does that. You know, or you could see that there was all these different kinds of discontinuities that we talked about last time, where there can be a limit, but that doesn't necessarily mean that's the value at that point. Or maybe if it's the kind of gap type discontinuity, well, there is no limit at that point, or whatever. You were quantifying all that last time. You got a question, Jared? Okay. There is, in fact, as is the nature of a mathematical course, there is a formal definition as to how all this works, but it kind of gets a bit annoying. I mean, we have to kind of work our way through a whole bunch of ways of quantifying closeness, as in a way of describing how close these functions are getting. Are they getting close enough as we get closer and closer to the value of x, or as we get closer and closer to the value of f of x? And the book makes these 4 bulleted points about what that means. Where man, it gets all jargony. I mean, like for example, the first of the bulletin points here says the absolute value of f of x minus L. What they're talking about here is this is the limit of that function, like it's the limit, as x is approaching some value a of this function f of x. It's going to be L, that's that limit. Which often is just a value f of a. Although, as we learned last time, it might not be. There might be those little gaps, or there might be those discontinuities, or whatever. And what they're saying here is, the difference between what is the value of f of x at that place and the actual limit is going to be less than some value epsilon. What they're saying is, no matter where you are on here, that error is getting smaller and smaller and smaller as you get closer and closer toward the value x is equal to a. Okay, there's always going to be some epsilon that is bigger than your error. Oh, that sounds like such a formal math thing. And in the same way, that distance between x and a, remember this is a limit as x approaches a, that distance is always going to be bigger than 0, and it's always going to be, there's going to be some number that's bigger than it. In other words, that distance will never be infinity or anything like that. Well, again, that sounds like such a pain in the ass. Oh man, you've taken enough math classes to know, myself included, that's kind of the pain in the ass thing, professors, like, they prove things like the error is less than infinity. Oh my gosh, well, who cares? These other things right down here are more actually just thinking through what the consequences of that means. Like if the absolute value of the difference between f of x and L is less than epsilon, it means that the value of your function at that place is between L minus epsilon and L plus epsilon. And this is just a little bit of algebra. I choose not to spend valuable minutes of our time on this planet showing you, but all we're saying here is that there is some, whatever that limit is, our value of f of x is between that limit minus epsilon and that limit plus epsilon. So as epsilon gets smaller and smaller, we're squeezing, we're pinching the value of that f of x is getting closer and closer and closer to L. As that epsilon gets smaller and smaller. Because f of x has to be between L minus epsilon and L plus epsilon. And the same game gets to work for this thing here with x minus a, the difference between x and what it's approaching, that a. It's another way of saying that x is between a minus delta and a plus delta. In case you didn't know that little thing there, that's a delta. That's a lowercase delta. Capital delta is the one you're more familiar with. It looks like a triangle. All right. Do I love this? No, I don't love this. But I see how then we use it to make a formal definition of the limit. Let's see where we're at here.
I have a question.
Yes, sir.
Is there a reason why you would have to use lowercase delta or?
It's just the way we use these. Yeah, we're just using it as a symbol. And traditionally,
I didn't know if there was a
No.
main reason why.
nope. You know all the Greek letters have capitals and lowers, right?
Yeah.
Yeah. It just so happens in the epsilon delta, or the formal definition of a limit, the symbols they use are the lowercase epsilon and the lowercase delta. We just freaked out the folks in the trig class the other day because there's a symbol that they're using that's lowercase omega, and they didn't love that symbol.
Looks like a W.
I know, lowercase omega looks like W, but it doesn't. It's an omega. All right. Anyway, they're using that on the problems on the current set, and they're not happy about it. Anyway, there's a formal blue box type definition here that shows that their limit exists for every value of this epsilon. There exists a delta that pinches it in. Now, this is really, really hard to see with this stupid definition. It sounds like, isn't that exactly what we've been saying all along? That there is this limit as x approaches a, there is some limit L. What does this actually do that's different? I like these graphs. What page are we on here? I like these graphs on page 185. Oh, I'm sorry, 195. Here's some function. See this function right here? Who knows what this thing is? It doesn't really matter for right now. That's our function right there. And we're wondering about this value a, where, you know, x is equal to a right here. We're wondering, what is this limit? As f of x approaches this, is there some limit over here, L? See this L right here? Now, in the formal mathematical definition of a limit, with epsilons and deltas, all along we've kind of just been eyeballing it. We're like, you know what, that's good enough. We can see as we get closer and closer and closer, we can approach from the left, we can approach from the right. They both come to a value, they both come to the same value, therefore the limit existed. And that was fine, and frankly that'll be fine moving forward. But again, I checked, and we do have to at least ever look through this. Notice how that idea of our x being like, there's some range it could be in, like from a minus delta over to here to a plus delta. There's like a little window we're talking about here. There is a matching up to that. There's like a little window around L. L minus epsilon and L plus epsilon. So like as long as we are talking about some value of x that's in this little range here, we'll be talking about some value of y that's in this little range right here. And so they are referring to a little piece of this function here that they have in common. Someplace a plus some little number will come across over to here to someplace in this range. And mathematically that is a pain in the butt to prove, but it can be done. But what they really want you to notice is what happens as those little ranges get smaller. Notice as we get closer into A, our little range here of A minus delta to A plus delta, it's a smaller little range here, and it corresponds to a smaller little range of possible results between L minus epsilon and L plus epsilon. So any place we pick in here will map over here to someplace in that little range. And the smaller and smaller we make these deltas, the smaller and smaller we make these epsilons, this little range that it maps to just gets smaller and smaller and smaller, and you can see where we're going. In the limit, the smaller and smaller we make those deltas and epsilons, we just pinch off to a tiny little area until eventually we hit the limit. And this makes math majors happy. And this makes math professors happy. That somehow they've more formally defined this. Okay? That it's like this little thing of pinching off. Now, they say, oh look, in this little electronic textbook there's an activity. You can visit the following applet to experiment with this. So let us do that. We go over here to this OpenStax thing. And it will let open. It opened earlier. Well, it's not happy now. Okay, that's alright, because what I was going to show you is, yeah, you can play, it has exactly these graphs. In fact, it might even be how they made these graphs right there. But they can play, and you can like make these values, you can stretch and make the value of delta bigger, or you can make it, and you see that as it gets bigger, this epsilon gets bigger. But, oh, this is it. Oh, it's a different function. It's still different than on my screen, huh? So like you can stretch out the values of these epsilons, and you can stretch out these values of deltas, and you can see as they get smaller, they pinch in toward a single value. Where did they go here? They pinch in. Okay, well anyway, something seems, that doesn't seem right to me. Anyway, but this doesn't look the same as it did when I was at home. I don't know if it didn't load up right or whatever. Anyway, the point is, this is mathematically nicer. And then your book wants you to actually be able to do this, to actually walk through and to be able to define what your value of epsilon and what your value of delta is and so on. So like for example, it shows you how to prove a statement about it. Like prove that the limit as x approaches 1 of 2x plus 1 is 3. And then they actually walk through, oh my god, look at their answer. So like this big in the blue line right here, this is their answer. Like this is what they think you want for your homework. If that was, what? 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 It keeps going. Does that sound like fun? Does that sound like that's leading us toward derivatives and integrals? Well, only in a very theoretical kind of way. And this is brief calculus. We don't need to get bogged down in all that. So it has a little problem-solving strategy here. you would have to work your way through these 5 little steps to answer a question. Now, they actually have another template here. Here's an example. Prove the same sort of thing. Prove the limit as x approaches -1 if this thing is equal to -3. And this one they give you like, put in the little, fill in the blanks. This would be a proof. Alright, I'm going to leave it to the students to figure this out as to how to plug in these steps into here. Now, then, they go through, oh my gosh, and they do the same sort of thing, well, the triangle inequality, and then they go through the same thing for right-handed limits and left-handed limits. We're not going to do any of those. Okay, and then they hit exercises. Crap. So basically, they just sort of opened up the giant textbook of theory of limits, which is a thing you could take in college, and they basically said, look how hard this is, now go do it. And that does not make me hugely happy. But like I said, we don't have any evidence as to how much we have to do, we just have to show that we've been here. So, your assignment is going to be kind of smallish. And it's going to mostly be something different than you're expecting. Hold on just a second here. Maybe I can get it over here more easily. This one. Hey, you. There you go. This might be better. So here's the problem set. I'll write this down over here. You might see over here. I want you to do page 206. Might be a little bit forward from there. I want you just to do 2 problems, 177 and 189. And I'll be honest, I haven't done them yet, but the answer in the back of the book didn't look terrible. But basically, they're just little proofs that you walk through the steps they give you. I mean, in the book, they show examples where you just fill in the blanks. Okay? You should be able to get those 2 to work. I ran out of time to do it myself. But then there's more. Go through the list on page 208 and identify the limit laws. I will show you what I'm talking about here. Page 208 is a list of vocabulary words in the textbook. It's part of the reviewing. There's page 208, here it is. Chapter 2 review, because we got a test coming up, possibly like a week from today. Now, some of these terms are things like, okay, we did more of application. We didn't do the applications about average velocity. And some of these things are awfully going to be useful, like learning about continuity, or continuity from the left, or continuity to the right. These are all things that could be on the test. But for our purposes of this assignment, if you dig through this little 2 pages of glossary or whatever here, a few of these things are those limit laws that we learned about last time or the time before. Find them. And write them out, or whatever. I mean, let's say you think discontinuity at a point is one of your limit laws, then write that one out. Okay? If you think the root law is one of them, then write that one out. Okay? Find the ones that match up to the limit laws we learned either in the last assignment or the one before. It's part of reviewing. Sound good? That's all you got to do this time. I don't need a ton of evidence that you've been in this section. Like I said, this takes it a little bit farther than we need for the purposes of brief calculus. Okay? All right, I'm going to pause this thing here.